This is E569 on Friday, October 11th, 2013.
Hello? Testing. Cool. All right. Can you hear me pretty clearly? Can everybody hear me? All right, cool. Hi, everyone. Welcome to EE569. Today, Professor Kuo will not be here because he is out of town in Korea for a conference. So I will be replacing him to give you a guest lecture, which is named Color Image Processing. So first of all, a little bit about myself. My name is Zhang Yang, and I am a final year PhD student at the University of Southern California. I'm a PhD student of Professor Kuo as well. So my research topics is also image processing, video processing, and I used to be a TA of this class for the past 3 years. So I'm kind of quite familiar with the content and stuff. And actually, I see some familiar faces who took the class last year, but somehow I see him again this year. And so I like to say that this topic, color image processing, this lecture is probably not the most interesting lecture throughout the whole class. So if you find, because it's a little bit old school, you'll see the content of stuff. So I will try my best to make it a little bit more interesting by showing you a little bit more video and stuff. But if you find it boring, it's not very uncommon because some of the content are really a little bit out of date. So here's the outline of this class, this lecture. First, we're going to go through a little bit background knowledge about what is color vision. A lot of things you have already studied in your high school physics class. So we're going to go through what is color, visible spectrum, and color systems, and also the color mixing. We're talking about additive color mixing and subtractive color mixing. In the second part, we're going to briefly go over a couple of color models. You're probably already familiar with RGB because you're dealing with some of the homework problems. I believe right now you're already working on homework 2, right? Is it? All right. Is it due today? Sunday, okay. Good for you, still have two more days. And then eventually we're going to talk about some applications about color image processing. We're going to talk about something you already covered probably in homework 1. I believe histogram equalization, sharpening maybe. And I've actually added a couple of content in the third part because I find that these are the applications that are probably 10 years back. So we are adding some of the interesting projects that the previous students have been doing. So I believe last year we actually let the students recreate the filters in the mobile app called Instagram. So we'll let them try to recreate all the color filters effects. And I'm going to show you some of the interesting homework problems that people come up with. And I'm also going to show you some of one homework assignment called the facial morphing, where you morph from one person's face to another animal's face. And this is actually one of the most popular and well-received homework problem in the past year. And I've been talking to your TA this semester. they think they will put the facial morphing problem in homework 4. So it's kind of preview for all stuff. All right. First, we're going to talk about what is color. So color is not a objective measure. It's actually a human perception. So it's actually not directly measurable. And what color a human being actually perceives is dependent on 3 different things. First of all, what is the light source? Is it a normal sunlight, or is it a tungsten light, or what kind of light source that is? And the second thing is, what is the reflectance of the object that this light is going through? So if this is a pencil, or is this an orange, or is this an apple? And lastly, it also depends on what is the receiver. Is it an image sensor? Is it an eye? Or is it a camera? So with that being said, let's take a look at a short video which explains better about what color really is. Operator, we might need an audio for that. Thank you. We're still waiting for the audio, I guess. I don't think I can hear it. There should be some sound at this point already.
One of the most striking...
Can you guys hear it? No, unfortunately no.
Give me a moment.
All right, thank you.
Can you try again?
All right.
properties about light is that it has...
Not really.
All right, give me a second. I'm going to pause.
Okay, no problem. All right, so before we get the audio, let's continue. And
Someone's coming over right now, so we should be able to...
okay, so the guy's coming?
He's coming, so once he's here...
Okay, cool, no problem. All right, I guess we just continue. And this is the visible spectrum. I believe that's something that everybody probably already know. So the visible spectrum includes multiple spectral color, which is defined as a light that is composed of only one single wavelength. And this is the visual spectrum. You can see, yeah, we needed audio for the playing. We play it directly from the desktop. Yeah, so. I believe.
Can you try it again?
Okay, cool.
One of the most striking properties about light is that it has color. To understand the phenomenon of...
I heard there, so it's coming through.
It's coming through, so...
Yeah, would you play?
All right.
of color, it helps to think about light as a
Oh,
wave.
yeah, that's there, yeah.
But before...
Cool, that's good. So what is the thing to control it? Okay, that's
You
good.
have to put the microphone.
Okay,
We're good, right?
thank you so much. Yeah, thank you guys.
No problem.
All right.
One of the most striking properties about light is that it has color. To understand the phenomenon of color, it helps to think about light as a wave. But before we get to that, let's talk a little bit about waves in general. Imagine you're sitting on a boat on the ocean, watching a cork bob up and down in the water. The first thing you notice about the motion is that it repeats itself. The cork traces the same path over and over again. Up and down, up and down. This repetitive or periodic motion is characteristic of waves. Then you notice something else. Using a stopwatch, you measure the time it takes for the piece of cork to go from its highest position down to its lowest and then back up again. Suppose this takes 2 seconds. To use the physics jargon, you've measured the period of the waves that the cork is bobbing on. That is, how long it takes a wave to go through its full range of motion once. The same information can be expressed in a different way by calculating the wave's frequency. Frequency, as the name suggests, tells you how frequent the waves are. That is, how many of them go by in 1 second. If you know how many seconds one full wave takes, then it's easy to work out how many waves go by in 1 second. In this case, since each wave takes 2 seconds, the frequency is 0.5 waves per second. So, enough about bobbing corks. What about light and color? If light is a wave, then it must have a frequency, right? Well, yes it does, and it turns out that we already have a name for the frequency of the light that our eyes detect. It's called color. That's right, color is nothing more than a measure of how quickly the light waves are waving. If our eyes were quick enough, we might be able to observe this periodic motion directly, like we can with the cork in the ocean. But the frequency of the light we see is so high, it waves up and down over 400 million times a second, that we can't possibly see it as a wave. But we can tell, by looking at its color, what its frequency is. The lowest frequency light that we can see is red, and the highest frequency is purple. In between, all the other frequencies form a continuous band of color called the visible spectrum. So, what if you had a yellow pencil sitting on your desk? Well, the sun emits all colors of light, so light of all colors is hitting your pencil. The pencil looks yellow because it reflects yellow light more than it reflects the other colors. What happens to the blue, purple, and red light? They get absorbed, and the energy they're carrying gets turned into heat. It's similar with objects of other colors. Blue things reflect blue light, red things reflect red light, and so on. White objects reflect all colors of light, while black things do exactly the opposite, and absorb at all frequencies. This, by the way, is why it's uncomfortable to wear your favorite Metallica t-shirt on a sunny day.
All right. So now we know that the reason why an orange is basically orange color is not because it appears to be orange, it's because all the lights except for the orange are mostly reflected. So this is the visible spectrum where you can see from the shortest wavelengths to the longest wavelengths. So on the right side of the longer wavelength is the area which we call the infrared radiation, where on the left side is what we call the ultraviolet. And there are 3 types of illumination lights, and which are achromatic light, chromatic light, and monochromatic light. So basically what achromatic light is what we call the white and uncolored light, very similar to what we have in the sunlight. The chromatic light might be a light of a mixture of different colors. So it's not a white light, but it does contain light of different wavelengths. Well, a monochromatic light is something that contains only one wavelength, and that's something what we can see in a laser light. The next term that we want to mention is, or a very important term, is called the spectral power distribution. This is actually a term that gives a characterization of different light. Basically, it's a function of lambda, which is the wavelength. So what it does tell you is that it tells you in this light, how much power does it have for each of the wavelength? Does it contain more power of red, or does it contain more power of violet? And here's some examples of the SPD, or the spectral power distribution. On the very left side, you can see the tungsten lamp. This is something what we probably usually see in a room, and you can see that most of the power actually is concentrated at the red region. So that's why you see it appears to be a little bit orangey, all the lights. And the one on the very right side is what we call the normal fluorescent. You can see that the power of all the wavelengths is relatively low. However, you do see some small spikes at the blue area. So that's why the fluorescent light appears to be a little bit bluish. And here's an example of an application of SPD. So we all know that when you take a picture of somebody's face under in a different scenario, it might appear differently. If you take a picture of somebody in a light room, or probably outside in the sunlight, the color of the skin appears to be differently. And that is because the appearance of the skin is actually a multiplication of two different things. The first thing is the reflectance of your skin. So basically what the percentage of reflectance of the skin tells you is that what wavelengths of light is more probable, has higher probability of being reflected. And this multiplied by the original SPD of the light source, this actually gives you the eventual color, skin color that is perceived by human eyes in that particular scenario. So in the previous video, we talked about why a pencil is yellow, why an orange is orange. Then the next very interesting to talk about is there's something that could be hard to describe what color that is, which is the mirror. So I actually found a very interesting video which actually explains what color is a video, what color is a mirror.
Vsauce, Michael here, and today we are going to talk about color.
Green, 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 green.
Hold on, let me just pink this up. Yellow.
Michael, aren't you going to come to the concert this evening?
I read about that. There's going to be a lot of purple there.
I didn't tell you about this earlier.
Well, look, I have to go around town first, but I'll be white, black. Colors.
Did you know that the human eye can differentiate 10 million different colors?
But what color is a mirror? You might say silver, because mirrors are often illustrated that way. And to be sure, they are made out of silver or silvery things like aluminum. But a mirror, in reality, is whatever color you point it at. In this green room, the mirror is green. And if you look inside a mirror, it becomes U-colored. An object is whatever color it doesn't absorb. These sticky notes are orange because when hit with typical white light, they absorb every other wavelength of visible light except for orange, which they diffuse into your eyeballs. But a perfect mirror reflects all colors equally. So in a way, you could say that a mirror is white. Except a mirror doesn't reflect colors in the same way that pigment does. A mirror reflects incoming light in a single outgoing direction. Specular reflection, not diffuse. This kind of reflection creates an image of the very thing in front of the mirror. So as bad astronomy jokes, a mirror is more of a smart white. But wait a second. That is a perfect mirror, and we live in the real world where there are no perfect mirrors. Every mirror absorbs a little bit of light. Not enough that it matters. I mean, looks pretty clear to me. But when you take a look at the spectrum of light reflected by a typical mirror, you will find that it best reflects light within the 510 nanometer range, which we perceive as green light. So technically, a mirror is a tiny, tiny, tiny bit green. You may have noticed this yourself when investigating a mirror tunnel. This happens when two mirrors face each other, reflecting the same scene back and forth and back and forth and back and forth. With each new reflection, a little bit more visual light is lost, but green least of all. That's why the reflection way down the tunnel is dimmer and greener. So maybe real-world mirrors aren't smart white, they're actually kind of green, but we should talk about white.
En español, white es blanco.
En français, white se dit blanc.
And in English, we have a word that comes from the same root, black, which is the opposite of white. How did that happen? Well, it turns out that all of those words come from the same ancient Proto-Indo-European root word, black, which meant shine, burn, flash. Some languages took it to mean the brightness of the flash, white, while others took it to mean what's left behind, the burned, black darkness. If you have blue eyes, your eyes aren't actually blue in the sense that the molecules inside them are absorbing all of their wavelengths of visible light and diffusing the blue. No, no, no. Instead, your eyes are blue for the same reason that the sky is blue, interference. In our sky, light from the sun encounters molecules of air. And because of the size of those molecules, light of longer wavelengths can slip on by. But shorter wavelengths crash into the particles, like blue light, and scatter, which is why we see blue when we look at the sky away from the sun. Without the air molecules, that space would just be black. And when direct sunlight has to travel through a lot of air, almost all the colors get scattered out except for the longest wavelengths, the red, which is what gives a sunrise and a sunset their color. The iris of your eyeball contains a hazy layer where light can be scattered just like the sky. Through a similar but slightly different process, shorter wavelengths are scattered more, making your eyes look blue, unless of course you have some melanin in that iris, in which case your eyes are going to be green, hazel, or brown. Enjoy those colors, and as always, thanks for watching.
Oops. All right. Hopefully you enjoyed the video. Okay, next we're going to talk a little bit about photosensitive cells. So the retina is a particular layer in the back of your eye that is in charge of perceiving the light and colors. And there are two types of cells basically at the, on the retina, which we call the rods and the cones. So there are around, if I remember correctly, there are around 125 million rod cells basically on your retina. And on a rod cell, it's very highly sensitive, and it is mainly in charge of sensing luminance, where the cones are more in charge of sensing colors. And as we said, the cones are less sensitive than the rods, and they're mostly in charge of sensing the colors, but they're actually not evenly distributed in the retina. So as you can see, depending on the distance from the retina center, actually the distribution of all the three types of cones, red, green, and blue, are actually different. When it's closer to the retina, you can see more green and more blue cones, where when it's far away from the retina center, you can see that there are actually more red cones. And one example of rods and cone cell is that a dog eye actually only have two cone type. So if you see the spectrum over here, you can see that, well, human being is able to see from red, orange, yellow, maybe green. On the dog's view, you can see that the whole thing is actually a single color. So what that indicates is that a dog's eyes is actually colorblind. And yeah, so the interesting thing is that I myself, my family is also give me this gene of I'm a problem differentiating red and green as well. So I guess I have a similar view, probably closer to the dog rather than the normal human being. The next thing we're going to talk about is luminance efficiency function. So basically what this means is that at a different we talked about this before. So for human being eyes, you perceive a different wavelengths of light differently, and this luminance efficiency function actually differs when your eye is dark adapted and when your eye is light adapted. Here's an example. So normally a candle flame should the way we perceive it, what we see is, we see the candlelight is always appears to be yellow. However, the spectrum of the candle flame light is actually red. And the reason why we look at the candle flame and saw it to be yellow is because the perceived luminance is a multiplication of the original radiant flux of the candlelight multiplied by the spectral luminance efficacy, which you can see here. So basically it's this curve that's going really up. It represents the spectral density of the candle flame. You can see that most of the power is actually concentrated at the red region. However, when it's multiplied by this curve, which is the SPD of the human eye, the result is actually, the peak doesn't appear to be around 700 nanometer, it actually appears around 580 nanometers. And that gives the appearance of the candle flame to be yellow. The other term we need to mention is called the metamer. So basically what this means is that two color which appears the same, they might have completely different SVDs. So it could be a green, but it could also be a mixture of different RGBs that appears to be green. Some characteristics of the colors. This might be very, you might be familiar with it if you use a lot of Photoshop, because in Photoshop when you want to select a color, normally people don't, some people use RGB still, but some people instead of use hue, saturation, luminance, because it's more intuitive for people. And so basically what hue represents is basically determines whether this is a red or is a green, the type of color. A saturation determines how strong, how full the color is represented. If it's a very soft red or is it a strong red. But brightness basically is a light red or is it a very a dark red. So let's look at a video about hue saturation. No ads.
Hi, I'm Nick. If you want to build your own website, then you need to learn HTML and CSS.
Hi, my name is Scott Naismith. I'm a landscape painter. This tutorial is about colour. Now, colour use is of massive importance in my paintings, and it's of a massive importance to know the theory about colour before you try and attempt to paint or design anything in colour. Every mark that you put on a design or you put onto canvas has three elements to it that make up that colour. It has a hue, it has a saturation, and it has a tonal value. So let's take the first of those, hue. Hues are all the basic primary and secondary colours that make up the rainbow. They are the colours that make up light. They're just wavelengths of white light. The primaries, yellow, red, blue, make up, in the transitions of those primaries, the secondaries, which are a mixture of two of the primaries. The secondaries being orange, purple and green. Now this rainbow of colour can be presented as a wheel. One colour wavelength at the end joined onto the beginning creates a wheel. Now what this wheel does is it allows us to understand the balance of colour so that we as artists and designers can use a harmonious colour derived from theories about this colour wheel. The most important thing to note about the colour wheel is what colours are opposite each other. These opposite colours contrast each other and are also called complementary colours. Tertiary colours are made up of three primary colours. Tertiary colours are not represented on the outside of the colour wheel. But what we must be able to do is identify where in the colour wheel a tertiary colour's hue line. For example, this warm brown here can be placed just between orange, red and red on the colour wheel. Saturation is how pure the hue is. To understand saturation, we must be able to understand how to desaturate a hue. To desaturate a hue, you need to add a complementary colour. You mustn't think of desaturating a hue as adding grey. Even though we're greying out the colour, we're not adding grey. I cannot stress enough how important this concept is. The main issue a lot of amateurs have with their colour use is the greying out of the colour, the deadening of the colour. You've probably heard a million times, don't use black, but at the same time, don't use a grey that you've just used white and black to mix a grey. Try to be a little bit more creative with the use of colour to create your unsaturated colours. I've got a quick demonstration of how two complementary colours can work. Often complementary colours side by side can jar together. They can they don't really look right together. You've probably heard the term red and green should never be seen. Often the two colours right side by side can be off-putting, but to separate them somehow can work. And we can separate them by the absence of colour, which is a grey, a neutral colour, a grey, a black or a white. If we look at the work of Matisse, you can do some research on the Matisse piece, The Snail. Towards the end of Matisse's life, Henri Matisse, he produced some cut paper collages, and on the snail he uses black and white combined with colours, saturated colours from all around the colour wheel. What he was trying to do was separate those colours with the use of black and white. So I'm going to use purple, and it's a blue purple, and I'm going to complement it with a slightly orangey yellow. Okay, so now I can show you what happens when these two colours mix. So what's happening here is that the two complementary colours, when mixed together, are giving us this grey neutral colour. Using the neutral colour, which is mixed from the two colours involved, is very important to keep in mind. So when you have a blue that you want to calm down a little and desaturate, you want to use a little bit of orange, or a colour which is based on the orange part of the colour wheel, like a burnt sienna. So what I've done there is just use two complementary colours, and then when they mix together they create the grey. By surrounding those very saturated colours with grey, it gives me what is known as a contrast of saturations. If we go back to the work of Henri Matisse, Matisse was considered as being revolutionary in his colour use. He was one of the founding artists of the movement of Fauvism. Fauvism deriving from the word wild beasts. And they were wild beasts of their colour use, and they used non-literal colour, but the colour was all based on theories and balance. Now they used very saturated colour, and the controlled use of saturated colour is very important. You can't just fire saturated colour onto a canvas or a design without consideration of what is being read next to. If you've ever wondered why the saturated colours or really bright colours look great in a black background or look great in a white background, it's because it's being read with a balance to something that has the least saturation. So saturated colours combined with unsaturated colours gives the saturated colours a little bit of a stage to perform on. Something's only hot when it's compared to something that's colder, and it's the same with colour, it's the same with painting. And this is what Matisse told us. Matisse was working with colours from all around the colour wheel in high saturations, and as soon as he combined it with grey, blacks and whites, he was able to then stop bombarding the viewer with all this colour information and give a balance of saturations. The concept of complementary colours creating grey provides you with a way of creating those greys to break up your saturated colours. I've got this painting here that I produced recently, and it's all about this theory. This is all about the complementary colours of blue and orange, and those blue and oranges are separated a lot of the time. We don't see the saturated blues right next to the saturated orange. The most saturated blues are in this section here, the most saturated oranges are here, but there's grey which stands in between those. So what's quite important sometimes is that we understand that you can't always put saturated complementary colours right next to each other. If you look at some of the work of Matisse and others, including some influenced artists by Matisse, such as Rothko, it's not a case of creating a vibrancy through putting one complementary colour right next to another. A lot of the time in Matisse's paintings, if you look closely, he'll separate those polar opposite colours, using a black, using a white, using a grey, and it creates a barrier between the two so that we can read them separately. Thanks for watching the video. There's going to be more parts to the tutorial on colour.
All right. Okay, next we're going to talk about color systems. So basically a color system is a way how we precisely to describe every color. And there are two types of system that you need to know. One is the more subjective one, and one is the quantitative one. The quantitative one is called SCIE, which is one that's very widely used standard today. While the subjective one, there are two different color systems. One is called the Munsell, and one is called the Ostwald. And first, this is the Munsell color system. So again, this is the way this color system is representing colors also by hue, saturation, and brightness, which you can think which is something similar to value. And we already talked about what hue means and what saturation means. And the difference between this Munsell color system and the second one, the Ostwald color system, is that it's the way that it's the color space, the way the color space is modeled. So, well, this one is more modeled as a I don't know how to describe it. This as a 3D cubic structure. Well, the Ostwald color space is modeled as a different structure. But and also in Ostwald system, it doesn't directly says hue, saturation, brightness. They use the term dominant wavelengths, purity, and luminance, which is actually similar to hue, saturation, brightness. And we talk about what kind of cells we have in the retina, and there are three types of dominant cells. There are rod cells and there are cone cells. And the perception of color actually depends on three major types of cones, which are red cones, blue cones, and green cones. What it means that every visible color that we can see in the world can be described or can be represented by a combination of all these three major colors. And this is what we call the RGB primaries. So color can be mapped by any combination of RGB. So given a random color of let's say C, you can it's a weighted combination of the G component, R component, and B component. And here are some color matching experiments. Basically what this means that this is an experiment where you see a particular color and you want to use three different types of lights, RGB, try to match towards. You don't know the weight of RGB, but you try to play with the weights and you want to try to match the object color with the combination that you come up with. So here is an example where you have the test light, which you don't know the wavelengths, but you try to match it with the RGB components. I believe here are some slides to show how this color matching experiment is conducted. The color on the left is the one we want, what we call a test light, where on the right side is we just randomly pick a combination of P1, P2, P3, which represents the proportion of RGB. And you see that the light is a little bit darker than the one we want, so we add a little bit of green, and you see the whole thing is lighter a little bit, but it's still a little bit far away. Probably we need to add a little more red. Oh, actually we add a little more green. So So this is the final combination. You can see that the combination light actually matches with the test light, and this is the eventual you can get. But normally in daily life, it's not easy to get the exact combination. We'll later show a video where an artist tried to match, really use pigment to match these 3 different types of pigments to match a test color, which is actually not that easy. Here's another experiment. This is a pretty reddish color, dark red. So this looks a little bit too pink. Maybe we need to add a bit more red. Or we reduce green. And here is a term we call the negative amount. So what this means is that if we add green on the left side, then we will match it with the one on the right side. By adding something on the left side actually is equivalent to subtracting the same amount of green on the right side. So by using this method, we can come up with that the final primary color is actually the one we have over here, which has positive red, positive blue, and negative green. Okay, so these are the subjective color system. Then we have the objective color system called the CIE. In CIE, we don't have RGB, we have X, Y, Z. So the Y is the component that matches what we call, talked before, the luminance efficiency function. And well, X and Z is more related to the chromaticity. And again, any color in a light, you can represent it by these 3 components, X, Y, Z. So I'm going to post this slide probably later on Den, so you could review it. I'm not going to go through the details, but the takeaway you want to get is that there are 2 types of system. One is objective, one is subjective. Objective is called CIE, and any color in the world can be represented by all these 3 components. But in an objective component system, these components are called X, Y, Z, where the other one, you use RGB to represent it. Okay, next we're going to talk about color mixing. We already see how we want to match all these 3 lights to mix them together in order to match the test light. And there are 2 types of color mixing, and which is the additive and the subjective. So for additive, it works for the RGB system, where the subjective color mixing works more for the CMY system. So CMY represents cyan, magenta, and yellow. So these are 3 different colors as well. So for additive color mixing, the primary colors are RGB. So the interesting thing here is that when you mix two lights, any 2 lights, the result light is actually appears to be lighter than any individual light. So this is in contrast to the subjective way we want to talk about later, because in that way, the more you mix, the darker it gets. So as you can see, if you mix all the RGB together, you will get a white light, and which appears much brighter than each individual light. And the reason why we call it additive color mixing is because if you put 2 lights together, the result of the light is a spectrum that is a combination of the individual lights. So let's say you want to mix red light with green light. So the result is actually you add all these 2 individual spectrums together, and that's how you come up with the spectrum of the final. I believe I have a very short video which is pretty interesting to show you about this. This is actually a little work you could do. Primary color RGB in this work. You see how the color is RGB. So yeah. So it basically tells you how you mix green and blue, how you mix red and green, how you mix blue and red. should be cyan, yellow, and magenta. If you really look at it. All right, so this is additive color mixing. On the opposite is what we call the subjective color mixing. So the primary colors, again, are not RGB anymore. It's going to be yellow, magenta, and cyan. And similarly to what we have for the additive, for subjective, what we get is actually, if you mix two lights together, the spectrum of the result light is actually by taking out the common parts of these two lights. So in this example, cyan light is mixed with yellow light, so they both have something in common, which happens between 500 nanometer and 600 nanometer. So that's why if you combine these two lights together, the result is green, which has a spectrum between 500 and 600 nanometer. And in this color system mixing, the more color you throw over there, the darker it actually gets. So this is actually very similar to when we are in high school and we're in kindergarten, when we play with pigments. The more color you put in and try to mix in, the darker it gets. If you put all the colors together, eventually it get basically black. So I believe I have another short video to show you how artists really try, and I'm going to show you how hard this color mixings really get in real life.
I'm going to try and match this colour here, this yellowy orange. So when you look at the colour wheel, you've got to try and see which colour on the colour wheel is closest to that colour. So for this one, well, it's a yellowy orange, so I'm going to start with the yellow. So if I just grab a bit of the yellow.
It is using RGB, but normally it should use cyan, magenta, and yellow.
I start to analyse to see, okay, which way is it now going to go? Well, it's obviously going to go towards orange here. When I hold that next to it, it's way too bright. So in terms of getting its hue, initially, that's the first thing we're looking to. I'm going to add a little bit more red to it. So when you're mixing colours, you only need to do a little bit. Yellow isn't very strong in terms of its tinting strength, whereas reds and the blues are a lot stronger. So I just start to mix that in together. Okay, and then I can hold it up, and then you look at the value of it and how light or how dark. Well, this is still a lot lighter than this colour here we're after, so I can still add a little bit more of the red to it, because red is darker in value than the yellow. If you took a black and white picture of these three, you'd see that would be, this one, red would be a lot darker. A bit more. Okay, and when I'm looking at this, I'm squinting my eyes. I'm trying to get it so that it isn't like a jump. When you hold it over it, you squint your eyes at it. You try and get so that this and this, merging together, so they're just one. Now, I know that it's not the ideal value yet. It's not the ideal tone. It's still a bit too light, but it's a lot closer than where we were to start with, just with this yellow. So now I look at the intensity, the saturation of it, and I can see, okay, this is still way too bright. So what I'm going to do is add a bit of its complement, the blue, to it. So again, I'm just going to add a tiny amount. See how it starts to go in its green? You've got to be brave and kind of keep on mixing. Okay, and now I'm looking at it, I'm thinking, it's still a bit too, it's a bit too greeny than this. So I'm going to need to add a bit more of the red. Okay, and that's looking pretty close. Now, when you are checking colours, it's always worth, putting a kind of swatch next to it. I usually do this on a piece of scrap paper. And then what happens with acrylics, as it dries off, it dries darker. So actually when I look at these next to each other, I can see that that's going to dry a little bit too dark. It needs a little bit more of the yellow. So you can just grab a bit more yellow. And you notice how I grabbed a lot more of the yellow than I did of the blue to lighten it, because the yellow isn't as strong. Okay, that's looking pretty good. This is Wilchem from Wilchem Art School.
All right. So you can see that if everything is digital, the only thing you need to do in Photoshop is probably to point the mouse towards the color, and you can see the combination of RGB. But whereas in the real world, if you're an artist, to match a particular color, you don't know the combination. You got to have to test it out, and there's a lot of variance in it. When the color actually dries out, it will become darker. So normally when you mix it, you got to make it a little bit lighter than the color that you want to mix. So when it dries out, it will match exactly. All right. The next thing we're going to talk about is color models, and I believe we're going to probably spend 10 minutes talking about it, and afterwards we'll take a short break, and then we'll talk about applications. Color model. So what time do you guys usually take breaks? What time does Professor Kroll usually take break? 10? 10:15? All right, cool. All right, we'll probably take a break earlier today. These are basically different spaces, and this is the way that we model a color in a 3D space. So we already talked about RGB, CMY. So these are all different color spaces in which we represent color. And the reason why we need different color spaces is because we have different applications. And for example, you guys are dealing with RGB already in your homework problem. But one of the problems with RGB is that it's so hard to know for an artist if they want to switch from a dark red to a slightly lighter red. They need to probably play with. They don't know how to play with the RGB, because to get it lighter, you need to play with different parameters together in order to get a lighter red. Whereas in a HSI or HSV, this is more intuitive. If you don't touch the H, the color won't change. If you just want the color to be lighter, what you can do is you can just lower the I component or the V component, and you can get from a darker red to a lighter red. So that's why for HSI and HSV, it's more user-oriented. And we're going to later talk about CMY. So the CMY space is more used for color printing. And what CMYK means is actually it adds an additional black region. What it's called key. It's a black component. And yeah, so CMY and CMYK is mostly used for color printing. Well, YUV is something if you're dealing with video compression, image compression, that's something people mostly deal with. All right, so these are a visual appearance of all these 3D color models. So RGB and CMYK is more modeled as a 3D cube, where HSI, HSV is modeled as a cylindrical model. And the other YUV and LAB, I'm not quite familiar with that, is modeled as opponent color spaces. RGB is the most simplest as most common lighting model. And as we talk about, RGB is actually additive, whereas CMY and CMYK is subjective. And the good for RGB is that it's very easy for programming, so that's why we use RGB in the homework problem. But again, the problem is with RGB is that it's so hard, it's so not intuitive. CMYK, we talk about it, it's used for printing, and the K is add to avoid that. So normally, in order to do black in printing, you need to add CMY together. And one of the problems if you use CMY together in a printing is that the paper will become really, really wet because you add too much ink onto the paper. So by adding a K component, you allow that if you want black, we directly add black. So we don't need to mix all these CMY together. It actually saves ink and gives you better printing quality. All right, I believe I have a little video to show you which explains the difference between RGB and CMYK.
Hi, I'm Ken from PressCats.com. In this episode, I'd like to talk about the differences between the RGB and CMYK color spaces. When should you use one instead of the other? And why even have two color spaces in the first place? Let's take a look. RGB stands for red, green, and blue, and is the format for video monitors, projection, web images, and most digital photography. RGB is an additive color space, which means that you add the red, green, and blue light to your black monitor to get all the colors. The more light you add, the whiter things get. RGB values are expressed as numbers between 0 and 255 for 256 possible values for each color. For example, you can get black, which is the absence of light, by having the value of each color at 0. You get white by having the value of each color at 255. In theory, that means that there are 16,777,216 possible colors with the RGB model. We can't distinguish them all, but it gives us a lot of flexibility. CMYK stands for cyan, magenta, yellow, and black. Well, the B was already taken by blue, so K will have to do. I'm just kidding. K originally stood for key because the black plate used to be used to register the others in CMYK printing. CMYK is the color model for conventional offset and some modern digital printing. CMYK is a subtractive color model, which means that you subtract light from a white piece of paper by adding more and more ink. The more ink you put on the paper, the blacker it gets. CMYK values are expressed in percentages. For example, white would be 0,000. Using no ink leaves the paper white. Black is a little trickier in CMYK because there are several ways to make it. You might try 0,00100 to specify straight black ink, perfect for clear, easy-to-read text, or 100, 100, 100, 0 for a black using the three other colors and no black at all. The problem is that too much ink on the paper makes it slow to dry and difficult to handle. Total coverage is a way of expressing how much ink you have on an area of your page by adding the percentages together. If you printed 100% of all four colors, you could get a total coverage value of 400%. In our previous example, we would have 300% coverage, 100% of each of our three colors. Most of the time, it's best to avoid exceeding 240% total coverage. With that in mind, let me introduce you to Rich Black. Rich Black is made using all four inks for a deeper black than is possible with K alone. At PressCats, we prefer 60, 40, 40, 100, but there are different formulas at every printer. If you get your printing done somewhere other than PressCats.com, ask them and they'll give you their magic numbers. So now you may be wondering, if CMYK is used for printing, why even bother with RGB? Well, good question. The truth is that although CMYK is used for printing, it's really not that efficient for other jobs. It's rather limited in its ability to display all the colors possible in RGB. In fact, CMYK is only able to print around 60 to 70% of the colors you can make in RGB. Many of the most vibrant and bright colors simply cannot be faithfully reproduced in CMYK. RGB is vastly superior for color grading photography. It tends to be more flexible when performing color edits and less likely to introduce color artifacts. RGB is also the color model for most digital cameras and offers a larger amount of plugins in programs like Photoshop. By doing your primary color adjustment in RGB, you will be preserving as much data as possible for your final image. As a side note, when color adjusting in RGB, it is often possible to view your color values in both RGB and CMYK. This can often be helpful for achieving color balance, which I will discuss in another episode. After your color adjustments are finished, it's time to convert them to CMYK. Converting your photos from RGB to CMYK before printing is a must to ensure the best possible printed output. Sending an RGB photo to a press can have unpredictable results as the color conversion may differ greatly from what you had in mind. This conversion step gives you the ability to control and refine final color output, and it allows you the opportunity to spot potentially troublesome color issues before going to press. If after the CMYK conversion you see unsatisfactory color shifts, it is a good opportunity to do some final tuning. For these refinements, the CMYK model will work fine. In fact, using the color sampler tool in Photoshop will show you the exact ink values that will be used in your printed piece. That, in combination with the selective color tool, can allow you to dial things in perfectly. Logos are an entirely different issue. Oftentimes, graphic artists will design logos with spot colors for brand consistency. Spot colors, also known as Pantone or PMS colors, are pre-mixed to exactly match preset standards. As an example, reflex blue is a spot color you might be familiar with. When a logo that has spot colors is used on the internet or on a television commercial, it has to be converted to RGB. When that same logo is used in 4-color process printing, it has to be converted to CMYK. All these conversions must be done with care so that undesirable color shifts can be minimized. For our purposes, that is going to press, CMYK is the model of choice. Before submitting your project for print, be sure all your photos, logos, background colors, and text are in the CMYK mode. Well, that's about it for this episode. I hope you enjoyed it.
All right. Cool. Sorry. All right. So that's RGB and CMYK. A couple of other very important color spaces you probably need to know. So for those of you who already taken 669, which is image video compression, you probably already know YUV. This is one of the most commonly used color space for video compression. Basically, what Y represents the luminance of the pixel, while the chrominance is converted to U and V. And the reason why this is very good for compression is because human eyes are more sensitive to the changes in luminance than in chrominance. So in compression, what we do is that we keep the resolution of the Y component, which is the luminance component, and we subsample the chrominance component, which is the U and V. So that's how the savings of you can achieve by doing compression. Yeah, so that's YUV. These spaces can be converted to each other. A lot of numbers here, you don't need to remember. Whenever you need it, just Wikipedia it. From RGB to YIQ, RGB to YUV, and from YUV back to RGB, it's very simple, just a 3x3 matrix multiplication. Some differences between YIQ and YUV. And again, HSI, which represents hue, saturation, intensity. This is a more intuitive space and probably very favorable among digital artists. So it uses a completely different structure. It's not a cubical structure again. It's a two-ended hexagonal pyramid structure. And it can be converted from between RGB and HSI as well. So the I component, which is the intensity component, is actually it's a little bit different from the way you converted RGB to the black and white pixel. So the I component is a average directly of R, G, and V. Hue saturation value, it's very similar to HSI model. And here's some details about how to convert from RGB to HSV, and from RGB to the CIE model, the XYZ component. And here's probably the last slide of, so to compare about, I think a lot of the details you don't need to remember, but some of the key takeaway you need to remember is the reason why all these spaces exist is because we have different applications. And we already, in the video, we already covered why CMYK is favored over CMY and why this is favored over RGB. But you also need to know that RGB, the reason why we use RGB is because it's probably the simplest form, and you guys already feel it when you do the homework problem. YUV, it's a format you need to know if you do compression, because it actually separates luminance with chrominance. And HSI, HSV is favored because it's very, very intuitive. You directly know, you can change the color by changing the H component, change the saturation by the S component, and change the, if you want to have a dark blue or a light blue, just change the I component. All right, so that's the first part of this lecture. I believe we take a break for 10 minutes and come back at 10:15, and we're going to talk about applications. These are all the theories. We're going to talk about a little bit of applications of color image processing. Hopefully I'm going to show you something more interesting. Thank you. All right. Can we close the door, Richard? All right, cool. Thank you. All right, let's continue. Cool. So that's what we covered in the first part is basically some basic background knowledge about colors and color models. The last part we're going to briefly touch upon color image applications. So in your homework problem, you basically all deal with black and white images. So every pixel is represented by a value from 0 to 255. But the problem will arise when you are dealing with a color image where you have actually three different values for each individual pixel. The question is, how are you going to deal with? Are you going to process each individual plane, RGB plane, individually and then combine them? Or are you going to change it from RGB space to another space and process in another space and convert it back? So here are some possibilities. One is directly apply on R. Let's say you want to do edge detection. You just do edge detection on R, edge detection on G, edge detection on B, and then try to combine them to come up with the edge map. The other way is you just convert it from RGB to HSI, and we know that I component represents the intensity. So what you do is you only do your processing on the I component and leave the H component and S component untouched. And after the processing, you convert it back to RGB, which makes sense as well because H and S are hue and saturation, which is not related to any intensity. So so these are some basic ideas, and but what to use really depends on what application you're going to do. Here are some sample color image processing applications, which includes histogram equalization, contrast adjustment, smoothing and sharpening, depth reduction, and edge detection and image segmentation. Okay. Here is an example of histogram equalization for a color image. So I believe this is probably a problem you guys already have, probably in homework 1, I believe. And the one on the very left side is the original image. And the one on the middle is if we apply histogram equalization on R component, G component, B component separately, and then combine them together. Well, the one on the very right side is the one we can first convert RGB to HSI. And we only do histogram equalization on the I component and then convert it back. So as you can see, I don't know which one you guys favor, but apparently the one on the right side, the color is just right. The one in the middle, the histogram is equalized, but there's something wrong with the color. You can see that the color is definitely quite different from the one from the original picture. So which is because you actually changed the RGB separately, and some of the color might be mapped to something else. Where in the HSS, if you don't touch H, if you don't touch saturation, the color will still stay the same. So this is an example of why you need to change to HSI and not just directly process it at RGB. Another example where you do contrast adjustment, the one on the first row is where you reduce intensity by 30%, 30 degree. And the one on the bottom is when you increase the contrast. So as you can see, the column in the middle is the one if you apply it individually on RGB. Well, on the one on the right is the one if you only apply on the I component. To be honest, I don't see much difference in this image, probably because I'm not that color sensitive. But if you see some difference, that's because, because the H and S is not touched. Here's another example of doing smoothing and sharpening for these two scenarios. All right. Okay. So one very important thing if you're doing photography is that you need to do a white balance. If you do black and white photography, if you do film photography, you don't need to deal with white balancing at all. But if you do color photography, you do need to do white balancing. That's one of the most important subjects you need to do. So when I was about 2 years ago, I was playing with film photography, and I was really working in a light room. So if you work work with digital, and white balancing is very simple because a lot of functioning in Photoshop already does the magic for you. Or you could just drag a slider, and you could do the white balancing. But if you're doing film photography, what you're going to do is basically you're going to go into the Lightroom, adjust the RGB component. It's actually cyan, magenta, and yellow, and create a print, wait for 1 minute after the print has came out, and go under the white light and adjust the color to the desired color. So normally it takes 10 to 20 prints to get a good final print for a film photography. So right now it's much easier if you're playing with digital. And one of the very easy way to do white balancing is what we call the gray world theory. So what you do is that this is based on the assumption that every picture in the world, if you take the average will be the same. A nice picture, the average of RGB will be the same. So what you do is you take the average of the RGB channel of the desired image, and you try to match that with the normal in the world. So this is a very easy way to do it, but that could cause some problems. For example, if you're taking a picture of a night sky, so if a night sky picture it's very dark, right? Only some stars are very light. If you take an average of that, it's going to be dark, but you don't want to match that with the average of the normal because it is a night sky picture. So there's definitely a problem with using the gray world theory. Yep, and here's some examples of, I guess, color correction. On the very left side, you do see that it's actually pretty dark, but the problem is that for white balancing, the most important part is you need to look at the region where it's white, and you want to really match that to white color. So if you see the shirt of this person on the left image, I think she's wearing a white shirt, right? And it appears to me that the one on the left side is a little bit, no, to me it looks a little bit blue to me. So your goal is actually to match, after white balancing, you want that shirt to look really white. So that's the goal of white balancing. The other application is called color depth reduction. And the problem we're dealing with, how do we map a 24-bit color image to a device that can only display an 8-bit color? And there are two ways to do it. One is called the color quantization. One is called the color halftoning. For color quantization, what we do is we basically we need to map different multiple colors to one single color. And what we do is one of the uniform way is that we assign 8 bits to the RGB component, and it seems that this method tried to assign 3 bits to red, 3 bits to green, and only 2 bits to blue. And so in this way, you can actually map a 24-bit to an 8-bit image. But this could cause a lot of problems, and the results might not look good. So there are other ways, more advanced way to do it. One is called using color map, and one is using an octree. So for color map, there are 2 popular methods to do it. One is called the popularity algorithm. Basically what this do is that it takes an image and create a histogram of all the colors. They try to pick the 256 most popular colors. And then for the other color, they try to group them so they try to take the popular colors and try to map the other colors to any of the popular colors. So for example, if in an image where, if it's a night sky, so the popular colors might be either very dark or very light. So all the other individual colors will be mapped to the nearest color that they selected. The other way is called the median cut. So basically what this method is doing is that it tries to align all the colors in horizontally try to find a window that captures all the majority of the colors, and try to split into the half, and then split it into the half for each individual half that we created. So by splitting it 4 times, you can create actually 8 different bins. So this is how you come up with the 8-bit representation. The other way is the arc-tree algorithm. So here is actually an example of how this is implemented. So for example, if we have an image, have a pixel value of RGB value 53, 187, 197, what we do is that we try to get the binary representation of all these 3 numbers. So we try to map them, lay out in a horizontal way. And the way we represent this number to a 8-bit is that we take every column and map them to one value. So this value is mapped to level 1. So this value is mapped to level 2. So in this way, all these 24 bits can be represented by 8 bits. So this is how the mapping is conducted. Color half-toning. Have you guys already done the problem of half-toning? All right, so I believe in your homework problem, you were dealing with black and white half-toning. So the problem with black and white is much easier because you only need 0 and 255 to represent the whole thing. But when it comes to color half-toning, what you need to think about is not only how many dots you want to place, how densely you want to place the dots, but also what kind of color you want to place for the dots. So a eventual image color can be represented by multiple color patterns. These represents the density of the dots, and the other variable you need to select is what color of the dots you want to play, so that you can try to approximate the eventual color. Some examples of color quantization. You can see that the 332 is that if you assign 3 bits to red, 3 bits to blue, green, 2 bits to blue. This one definitely has probably the poorest result. And medium cut is a little bit better. Arc-tree performs all right as well. And all these methods, if you use error diffusion, and you can actually see that you can get a pretty smooth result after the error diffusion. Some other image processing applications, color image segmentation, and color edge detection. Yeah, I think these are something we just briefly introduced right now, but you could, if you're interested, you could definitely look it up later online. Pseudo-coloring. So this is an application very commonly used for people dealing with biomedical. So because all the images they're dealing with are black and white images, but sometimes people need to spot, as a doctor or as a researcher, you need to spot the tiny details, and it's more intuitively, it's probably better if the black and white image can be mapped to a color image, so you can actually see the similar regions. So that's why we need to map from a black and white image to a color image. There are different methods to do the pseudo-coloring, which includes intensity slicing and gray level to color transform. These are the 2 major methods. What intensity slicing is doing that is basically trying to place a plane on top of it. If your image, if a pixel is above particular brightness level, you assign a particular color to it. So normally the common way to do is the higher the brightness is, the redder the image is, and the lower the value is, usually you see a blue region. So that's how you map from one region to the other region. So as you can see on the very left side, you don't see, you only see the the approximate shape of the object, but a lot of the details you cannot actually spot on the left side. But after you map it from the black and white to the color image, you can actually see that there are a lot of things going on actually in the structure, and this is why the application is so important. Good. Besides the slicing method, there is also, you could do the transformation on each individual planes separately. You could do the red transformation, do the green transformation, do the blue transformation, then combine them together. All right, and here is an example of an eyeball, I believe. And so in this example, I believe the higher the intensity, the more bluish the result is, where the lower intensity is mapped to the red colors. Okay, so that's the first part of this lecture. That's normally what Professor Cole had me to talk about, but since I believe I wanted to add some other applications, so I put out some additional slides. Last year we actually had we have designed an image processing problem for the students, which is very similar, very, very close to color image processing. And this is what we call the reproduce Instagram. Just a little survey. How many of you have heard about Instagram or have used Instagram before? Just raise your hand. All right. So how many of you actually use Instagram to take pictures, upload it every week, at least once every week? Can you raise your hand? All right. So the funny thing is that, so I mentioned Instagram in 2011, so it was 2 years ago, and there was only one student who raised his hand actually, who has heard about Instagram. So last year when I asked the question, I believe there are 3 students who raised their hands. So I believe after last year taking the class, and the acquisition by Facebook happened, so everybody probably heard about it from that scenario, and so that's why today I actually see half of the people actually using Instagram. But the other interesting thing is that my friend is doing a startup, and he's actually doing customer development, going all around the campus asking people's questions about what are the most popular apps you use on your phone. And from the people who he interviewed are mostly people who are undergrads, and the top 1 answer is Facebook, and the top 2 answer is Instagram. So a lot of, especially in the undergraduate community, Instagram is something that probably definitely people use every day. So I'm actually surprised that nobody, when I asked the question, how many of you actually uploaded pictures every week, once every week, nobody raised their hand. I guess probably you guys are graduate students. All right, so the problem we designed last year was in Instagram you have all these kind of filters called, I don't know, I forgot the name, like Kevin, Pro, all these kind of fancy filters, but it's kind of a black box. So what we want to tell the students is that, can you give you an image, can you recreate all these filters that Instagram has? You don't know what's happening, but we want to try to hack into it and try to figure out how Instagram did all the filters. So this is an image that was created by one of the Instagram filters, and we said, can you recreate it? And here is a basic diagram about how you can do it, how you can do the magic. Basically, the most key important part is that you need to do the color mapping. You need to split the RGB image into R plane, G plane, B plane, and apply a different transformation function on each individual frame, so that you could actually get a kind of a image that is color filtered and the color tone is different. And then if you use Instagram, you'll know that they have a lot of fancy stuff. You can add some sort of a background effect and add some sort of a border effect, which make it look a little bit hippie in the final leaf. So I'm going to quickly go through what's going to happen. So I don't think this problem is going to happen probably this semester, but you could do it if you're interested. And you can always, whenever you go out and interview, when people like to ask you what is the thing that you have ever hacked into, and I think this is, if you have tried out this one, it could be a good story to tell. So although the Instagram looks kind of fancy, but the color mapping is not fancy at all. What you actually need to do is you need to figure out what kind of curve that's going on in Instagram. And the x-axis is from 0 to 255, while the y-axis is 255, 0 to 255 as well. So basically, what this curve tells you is that given a input image of a blue pixel of, let's say, 127, what value 127 should be mapped? So you need to figure out for all these 0 to 255, how is it mapped? Once you figure out that, all the rest is kind of simple. And what we do, the magic trick we do here is that we want to figure out how the mapping is done. So we use a probe image, which is which contains 64 squares region with values of 111, 555, 999, all the way until 253. We process this probe image using the iPhone, using the Instagram app, and come up with the response image. So now, since we know the probe and we know the response, the rest of the work is we need to know if this one mapped to this one, then what is the corresponding value in the transformation map? And okay, here's an example. So if we know that this is 111, and it maps to 324. So what this means is that for R, 1 maps to 3, and for green channel, 1 maps to 2, blue channel, 1 maps to 4. And if you do this for all the 64 values, you can actually get a coarse mapping rule by mapping them 1 by 1. But this only shows 64 values. We have still a couple of values missing. And we use some sort of interpolation method to interpolate all the values. So if you combine all these dots, you basically see that there's a fine mapping rule. You can map all the 256 values. So this is how, using all these 3 rules, you could map from one original image to an image that looks kind of an Instagram effect. Last part is pretty easy. You add some sort of a grainy effect to it and add some sort of a border, and you can come up with a final result. And some other recipes, we actually give the students a lot of other border effects and grainy effects, and you can see, you can create different effects afterwards. And for bonus problem, we actually ask people to reproduce all these 6 Instagram filters, and if people do it, they will get some bonus points. And we also encourage students to actually design their own filters, and I would like to show you a couple of, okay, in Instagram there's also some like out of focus effects, and you guys already did the 5x5 mean filter, whatever filter. You could just do a blurring and just de-blur the focus point and blur all the other regions. So you can, this is how you can create the out of focus and in focus effects. All right, I would like to show you, this is the fun part, I'd like to show you a couple of filter designs of previous students. So the requirement is you should not use any of the Instagram filters. You should design your own one. And the more creative you are, the more bonus point you can get. Students can get up to 5 bonus points in that problem. So we got like half of the people in the class actually submitted their designs. So we have selected some of the pretty cool ones to show. This is for first example. It's called the oil painting filter. This is by a student. So apparently he used some sort of a, I don't know, a medium filter maybe to create a oil painting effect. This is another submission called the Warhol filter. Apparently it comes from Andy Warhol. And yeah, it's also pretty creative. This is the pencil edge filter. I think it's a combination of edge detection, edge strengthening, and some sort of smoothing in the background. And this is the cartoon filter. This is another example of the cartoon filter. This is the SC splash. I think it's kind of it's a very small filter. It only filters out blue, magenta, and yellow, and just leave everything else to be black and white. This is a shadow filter. Vincent filter. This is the balmy filter. I don't know if you can see it clearly, but it definitely adds some sort of a grainy effects on the back. But the next one is my favorite one. It's called the rainy day. I think it's very beautiful, and it gives you a lot of memories comes back whenever you this picture kind of blurs the whole image, and then adds a window with the rainy drops on top of it. So I definitely think that this is one of the most artistic submission in last year, and it's definitely my favorite. I don't know about you guys. And some other submission without a name. Yep. Cool. I think that's the last one. All right. Okay, so so that's actually the first problem that we actually encourage students to submit their own creativity. And in the E569 in the whole course, we actually have another problem, which is pretty famous for. If you actually walk into the EEB building, there's a big screen which shows some of the stuff related to WE, and we actually show some of our student submissions of last year on that particular screen. So this problem, this problem usually appears in homework 3, and I just talked to the TA of the semester. I think this problem is going to happen in homework 4 for you guys, so be prepared for that. So this is actually my favorite problem. This was actually my term paper project when I was taking this class back in 2009. So I just wanted to find something cool, something interesting, so I picked a topic where you can morph one image person's face to another person's face. And afterwards, it becomes, when I first time became a TA, I designed this problem to be a real homework problem. And then afterwards, we design it as a bonus problem where you can submit not only an image, a facial morphing image, but also we want you to come up with a facial morphing video, and you should choose your own subject. So it's a lot of fun. So today I would like to show you some of the selected works of the previous students. So the way we graded this problem is very, very, very fair. We have a voting committee of normally 30 people. They're students from the previous TAs and graders of this class. We have students from Cinematic Arts School. We have students from Design School. And last year we had Diane Demetrius and also a teacher from the Computer Science Department for the CSCI 520, which is computer animation. So he's kind of, the space very well. So we have all these kind of people to vote for the best video they want. And we pick the top videos based on the votes and give them bonus points. So I'd like to show you some previous submissions. This is the submission of 2 years ago, I believe. Get better and better because we're sorted by their rank. the last one, originally we thought he was cheating because it looks so smooth. And actually, I asked him how he did it. There's no trick in it because he just divided the whole face into a lot of triangles. The more triangles you divide into, the more frames you created, the more smooth your result is. The funny thing is, the winner is actually not a WE student. He's not a computer science student either. He's actually a biomedical engineering student. So that was funny. Yeah. So this is what happened 2 years ago. And last year, we showed this video to all the students. We say, you guys could do better. You guys have to beat the number one in order to win this year. So I'm going to show you what's actually displayed in the lobby of WE right now. This is what we have last year. That was Diane's favorite, actually. So this year, I think the top two videos are created by two PhD students from WE. So yeah, and the last one, actually, a lot of people like it because not only it's created very smoothly, technically very good, the images are very well chosen, and also a story. You see 4 different Bonds, James Bonds, together. So so hopefully it'll give you some inspiration for you guys for homework 4. So hopefully you guys could do better. You guys at least need to beat all these two batches, because you already see all the previous submissions. Yeah, so, and the fun part, I actually TA'd for other classes as well, but this class is specifically fun for me because we all have these kind of bonus sessions where you can see students having this bonus problem only worth like 10 points, and if you don't get any votes from people, you don't get any bonus point. But we still see that so many people are spending so much time. You could spend like hours and hours working on the last video. You see it. You only have to enjoy it, to be willing to spend the time. And this is what we see when I teach a class. What I like about it. And I think the goal for actually teaching the class is, for you guys, is probably not really learning the knowledge on the textbook. It's really inspiring. You feel you're really interested in image processing. So hopefully, if you want to go for a PhD in image processing, that could be a starting point. If you want to be a researcher for image processing, this could be a starting point. So I think that's the goal of education, from my perspective. Cool. So what we showed so far. So what we showed so far, everything is still in the previous class projects and school projects. But next, I'm going to probably show you a little bit of thing about what's going on really in the industry. Because when you're being a student in the school, you kind of only focus on what the teacher said, what the assignment says. You don't pay really attention to what's going on outside. So I would like to show you 3 different applications which is related to image processing that's happening in the Silicon Valley, which is one of the coolest things to talk about these days. The first thing is called literal. How many of you have heard about literal before? All right. How many are you guys using literal? Okay. Have you guys thought about buying a literal maybe? Thought about it. How much is it right now? Like $3.99 is what I believe. Yeah, right. So literal actually started out as a PhD thesis, actually. So it started out from a PhD thesis of a Stanford PhD in, I believe, in either computer science or EE, but his major or research focus is on computational photography. So that's how literal actually came out. So what this literal is trying to deal with the problem is that when we take a picture with our smartphone or with our camera, you have to have a focus plane. You have to focus on something. And many of the times, kind of a problem that we're dealing with is that the person you want to focus on is not in focus, especially when you go to a tourist place and you want to give your camera to somebody else, especially some old people who doesn't know how to use the camera. They will just, when you want your face to be in focus, they actually focus on the background, and then your face is blurred, and you can do nothing about it. So what literally trying to solve the problem is that when you click a button, you don't need to focus. Every plane field, focus field is captured, and you could focus afterwards when you come back to home. So that's the magic of it. So let's see a little video about it.
Hey, my name's Chris. I love taking pictures, so I was pretty excited the first time I heard about the Litro camera. Now that I got my hands on one, I want to introduce you to an entirely new way to take and experience pictures. The Litro camera can capture the entire light field instantly, which means you can refocus your pictures after you take them. And one of the best things about this is you can take advantage of all the depth in a scene and take what we call living pictures. Pictures you can really interact with. Hey guys. Hey. Okay, here's a good tip. I'm going to take a picture of my friend Katie. So I'm going to zoom out until the zoom slider is all the way to the left. And then I'm going to move in super close. And I can tell I'm close enough because the flower is starting to get visibly out of focus in the foreground. And this amount of blur is actually a good thing. So when I go back and refocus it, it's going to look really cool when I share it. Let's try this. Perfect. So I can refocus on the flower, on Katie, or even the Golden Gate Bridge in the background. Nice. Okay, so my second tip is on shooting portraits. Now, if you're a little further away, zoom in, moving the zoom slider to the right. And I'm going to get Nicole's face in about a quarter of the frame. And to get the most interesting living picture, try to frame up multiple things in the shot. Perfect. So that's a living picture. Nice face, Steve. Since it turns on instantly and there's no need to focus, the Litro camera is great for taking quick snapshots. I mean, I pretty much take mine everywhere I go. Make sure to check them out on your computer. And of course, share them with your friends. That's pretty much the basics. Now, if you want to learn more advanced features, check out our video on creative mode. Happy shooting.
So basically it gives you a basic introduction of the electro camera. And one of the most important things when you design a product is that you need to do the marketing. And one of the great ways to do a great marketing is to create an interesting story out of it. So I'd like to show you another 1-minute video which tells a great story about this product. Pretty sweet, sorry. Yep. Cool. So this is the product, but one of the problems, I think you guys need to think critically about this product. It's cool, but one of the problems that this product imposes is that you need to buy a separate camera, and it's not cheap. It costs you about $400 to buy that particular thing. How many of you, if you know the product, how many of you will really purchase it? That's a big question. And it's not a very cheap thing. So it might be targeting at a particular niche market where people just like to be really hippie, but it doesn't really focus on the mass market, the general public. So the next product or next application we want to talk about is try to address this problem. Right now, everybody has most of the people have a smartphone. And the question we want to ask is, what if we can add this technology and create it as an add-on to your smartphone? So you could apply the technology directly as a post-processing technique on your smartphone. So this is what I found. This is called Pelican Imaging. I actually don't know about this startup before, but I was recently know it from my friend. So what this application is doing, it tried to add a little bit add-on onto the camera of the smartphone, so that you can actually recreate all the after focus effects just using your smartphone. Let's take a look at the video.
The camera inside your cell phone is getting smarter. With the next generation of smartphones, you can't take a bad picture. There is an integrated array of cameras, so every pixel is in focus. You'll never miss the perfect shot. Because every pixel contains depth information, you can select any 2 points to measure the distance between them. When you capture video, your phone or tablet can actually use the data to build a 3D model. What you do with that model is up to you. Create a digital avatar, or plug it into a 3D printer to create a personalized gift. Use your creativity, along with a smart camera in your smartphone, to make every occasion more memorable. Pelican Imaging.
So I have to tell, the demo looks cool, but the 3D printing part is fake. Because if you look at it really, go to Maker's Fair to look at the 3D printing, it comes with one color, and it won't create the statue you will see in that, but it's just for demo purposes, I believe. So this is actually a PhD work as well. So the technology behind this project was actually published as one of the best conferences in the computer graphics community called the SIGGRAPH. It's actually was published in SIGGRAPH Asia 2013. So I actually found the technical video description of this technology. So let's take a look at it.
PICAM, an ultra-thin, high-performance monolithic camera array. The main problem in designing cameras for mobile devices is the limited space for the camera lens. With a larger lens, as in the digital still camera on the left, higher resolution and quality can be achieved. In today's thin phones and mobile devices, there is little space for a large lens with many optical elements. The camera's quality must be compromised in order to deliver a thin industrial design. The focal length must be shortened, and the size of the sensor must be shrunk to fit the camera in the phone. A typical smartphone and the profile of one of today's camera modules are shown on the right. We call today's camera the legacy camera. A high-resolution legacy camera is shown on the left and typically contains a single image sensor integrated with a multi-element lens stack. There is usually an autofocus actuator built into the lens stack to enable autofocusing. A Bayer color filter array on the focal plane enables the pixels to capture color information about the scene. In our array architecture, which is shown on the right, we divide the single lens into multiple lens apertures. Each lens corresponds to a subsensor on an underlying sensor array. Each subsensor is designed to be independently controlled to maximize flexibility, and the individual sensors are optically isolated from one another. Additionally, the color filters are a single color for each camera, which eliminates color crosstalk. The raw data from our camera is read out over an industry-standard serial MIPI interface and is processed through a software pipeline to synthesize a high-resolution color image. In addition to the color image, we also generate a high-resolution range image or depth map. In order to form a final high-resolution image, we must correct for the differences in parallax among all the cameras. On the left, we show the resulting image if parallax is not corrected. The final reconstructed scene will have significant artifacts. Therefore, we must compute a depth map shown on the right to determine the depth of objects in the scene. With this depth map, we can correct for the parallax and generate a consistent reconstructed image. On the right, we now show the results of the restoration after the parallax is corrected. Once we have the depth information, the restoration stage of our pipeline can begin. Pixels are fused from each low-resolution camera into a common high-resolution grid. Here, we show pixels from the green cameras being used to seed an initial estimate for the green high-resolution image. The cameras are placed onto the grid, one by one. Here we show the rest of the reconstruction process for the green channel. Once the pixels are fused onto a common grid, any remaining holes are filled, and this is our initial estimate for the subsequent map restoration. The initial estimate is then refined using a map estimation algorithm, which incorporates prior information about the camera model and imaging statistics to form an optimal reconstruction of the original scene. Finally, the restored image is shown in color. PICAM enables applications beyond traditional image capture. Because the lenses have a short focal length and hyperfocal distance, the images which are captured are almost entirely in focus. Here we show the all-in-focus image, which is captured by default. The availability of a depth map enables PICAM to compute synthetic focus effects. The images can be refocused after they are captured. Here we synthetically focus at near, middle, and far distances. PICAM can synthetically refocus video as well. Here we maintain focus on the moving target as it moves around a toy train track. In this application, we generate synthetic viewpoints from virtual points along the array's aperture. All the information is captured in a single snapshot, and intermediate virtual viewpoints can be reconstructed digitally in post-processing. The motion parallax seen here allows one to get a qualitative sense of the depth of the scene without having to wear any special glasses. Finally, the depth map allows PICAM to capture and model real-world objects like this Chinese dragon. The points from the depth map are projected into 3D space as a point cloud, which can later be processed with triangulation, mesh generation, and other 3D modeling algorithms. We believe this depth information will enable compelling applications such as Z-keying and augmented reality. This will allow one to mix real-world objects with synthetic objects for applications in both gaming and commerce. We believe that our approach represents a new paradigm in imaging which combines a unique form factor with the ability to compute depth. PyCam will enable richer interactions with images going forward. Thanks for your time.
All right. Cool. So, yeah, so you definitely see that this is a very great example where you apply the knowledge in the academia to an industry application. So, and it's actually very related to image processing. Probably not very related to what you're studying here, but all the stuff you're studying here are just the basics and knowledge. But what you learn here is that will be leading to much more advanced in the future. The last application I want to show you is something it's called leap motion. And how many of you have heard about leap motion? All right. How many of you have an HP computer that has a leap motion? All right. Would you guys ever try to? What kind of application would you use for leap motion if you buy it? What? For gaming, okay.
They use for SpaceX, they developed that tool where they're like designing the cat designs.
Oh yeah, yeah. Cool. Yeah. So leap motion is last year when I was in Silicon Valley for the summer, it's basically something that everybody was talking about. So all my friends, when we're having dinner, a lot of my friends who work in Google and work in other startups, they all talk about leap motion. They all talk about, have you heard about this? It's something so new, so cool. And I did look into it. So and it's really different. It's a combination. Basically, it's a how to define it? It's a Kinect, but you use the technology of Kinect, but at a much finer resolution, and you control everything you have on the screen. So I believe this is like a startup that started in 2010, and a lot of you definitely wanted to land a job in a big company like Google or Facebook. But my friend actually who worked in Google, she actually interviewed for this startup as well, but she couldn't get in, but got into Google. So this is definitely a good startup to watch, and they have a very, very cool demo video to show. Basically a very small box where you put in front of the screen, and you could do any kind of gestures. At least in the demo it shows that you could do any kind of gesture just above this little box, and the whole screen or the control will just react towards your action. So it's kind of like doing Kinect, but using your hands with a much finer resolution. So this is a video that initially when they created for demo purposes, but the question probably is, how do you use this leap motion in a daily life? Or if you have a Mac computer or you have a Windows computer. And here's an example of if you're using leap motion, how you combine that with a Windows system. Tells you how you can open up the email, browse the content, browse the news, and how you zoom in. Cool. Yeah, so that's probably the last thing I want to show you today. This technology has already been implanted into the latest HP computers. So I believe if you buy any of the latest models of HP computers, you could potentially experience this cool technology. I don't know how it goes, but I know one of the founders, the CTO, is actually, he used to be a PhD student from University of North Carolina, but he dropped out. He's kind of a major of physics and mathematics. So that's also the technology behind. It's definitely not computer vision. It's definitely related to what his PhD studies about. And I have actually a friend who works there, and he told me that they actually have a bunch of image processing engineers in the team. So this is definitely also a very cool startup related to image processing. So if you guys considering working, need to find a job after graduating, that's something you want to consider. Cool. So I've nothing to show you. I believe we can end up early today. So hope you have a great weekend. Hope you enjoyed the lecture. Thank you.
Exhibit E 569 on Friday, October 11th, 2013.